We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India.
Hello and namaskar to all the viewers. Today I am going to share some technical information related to stress strain diagram of WRCB. Before I switch over to stress strain diagram of WRCB, let me tell you something about MU limb. MU limb means limiting moment of resistance. In my last lecture, I have used Fe415 and I have mentioned the equation MU limb is equal to 0.138 FCK BD square. So looking at that equation, some students might confuse from where that equation comes, or if Fe 250 or Fe 500 are given, is the equation remains same or it changes? So let me clear that doubt first so that it will be easy for all the students. So for Fe415, I have written MU limb is equal to 0.138 FCK BD square. We know that in IS 456 page number 96, yes, IS 456 page number 96, they have given the equation of MU limb. MU limb is equal to 0.36 XU max by D 1 minus 0.42 XU max by D BD square FCK. Now, what about this XU max by D? In IS 456, page number 70, they have given the value of XU max by D for various steel grades. And it is if Fe 250, then the value of XU max by D is 0.53. If Fe 415, value is 0.48, and if Fe 500, then value will be 0.46. This is already given in IS 456 page number 70. Now we are using Fe 415. So what will be the value of XU max by D? 0.48. If we calculate this, you will get the value 0.138, then remaining is BD square FCK. So in this way, we can calculate the equation of MU limb is equal to 0.138 FCK BD square. Now let's see for Fe 250, what will be the equation of MU limb? Again, the equation of MU limb will remain same as it is given in IS 456 page number 90. For Fe 250, what will be the value of XU max by D? It will be 0.53 into 0.53 bracket 1 minus 0.42 into XU max by D is 0.53 BD square FCK. When you calculate this, you will get the answer 0.148 BD square FCK. Means if steel grade is Fe 250, then equation of MU limb will become 0.148 BD square FCK. Similarly, If we use Fe 500, what will be the equation of mu lim? Again, we know mu lim is equal to this equation already given in IS 456.36. For Fe 500, what is the value of axiom x by d? It is 0.46. 1 minus 0.42, 0.46 dt square fck. When you calculate this, you will get the answer 0.133 dt square fck. It means for Fe 415, value is 0.138. For Fe 250, value is 0.148. And for 500 grade of steel, value is 0.133 fck BD square. So in this way, we can calculate the equation of mu lim with using the equation which is given in IS 456 page number 96. Right? Now let's come to the topic stress strain diagram. So here I'm going to explain the stress strain diagram of WRC beam. So when we heard the word stress strain diagram, the common question comes into our mind is what we get from the stress strain diagram, or what is the use of it, right? So from stress strain diagram, we get the behavior of materials. Yes, I'm talking about behavior of material at different stages of load. Means when we apply the load on the material at different stages, how that material will behave. We get all the information from the stress strain diagram. And in this lecture, we are talking about stress strain diagram of WRCB. It means we are going to learn how material in the WRC beam, materials are only two, concrete and steel, means concrete and steel, how concrete and steel will behave when load is applied on the WRC beam. So for that, let me draw the cross section of WRC beam. This is width of the beam. 1, 2, 3, and 4. Reinforcement in tension zone. This is effective depth. This is AST. This is neutral axis. And this is a steel in compression zone. Right. This is effective cover in tension zone. E means effective cover in tension zone, and D dash means effective cover in compression zone. Below the neutral axis, zone will be in tension, and the upper side of neutral axis will be in compression. This is cross section of WRC beam, and this is ASC. Now let's first draw the strain diagram of the WRC beam. So strain diagram of WRC beam will look like this. So first we will see what does this 0.0035 means. 0.0035 is the maximum compressive strain in concrete. It means when load is applied on the beam, and in that beam compressive strain goes beyond the 0.0035 value, beam will fail in compression. Now again, it will quite difficult to visualize the failure of beam in terms of strain, right? So let me simplify this. We know that strain is equal to delta L upon L. We already know this. Strain is equal to delta L by L. Suppose length of the beam is 3 meter. So obviously 3000 mm. Now here, what is the value of maximum strain? 0.0035 is equal to delta L upon 3000. That's why 0.0035 into 3000 is equal to L. We get delta L 0.0035 into 3000. So we get 10.5 mm. Right? Now it is clear to visualize. It means what? When beam is subjected to load, and due to that load, if compressive deformation in concrete goes beyond to 10.5 mm, means compressive deformation goes beyond to 10.5 mm, beam will fail in compression. So this is the simplest explanation of 0.0035 strain in terms of deformation, right? Now, in this from this diagram, we can clearly see that at the top of the beam, the strain is maximum. When we goes down, strain gradually decreases. And when it reaches to neutral axis, yes, when it reaches to neutral axis, it will become 0. And when we come down from that neutral axis, obviously what happens here? In other words, we can say that below the neutral axis, tensile zone starts, and tensile zone is all about tensile reinforcement. When we goes down beyond the neutral axis, tensile strain starts from 0 to, and it starts to increase, and it becomes maximum when we reach at the tensile reinforcement in the tensile zone. Again I repeat, when we reach at the neutral axis, compressive strain will be 0, and we go down from the neutral axis, tensile strain gradually increases, and it becomes maximum where tensile reinforcements are placed. And 0.87 Fy upon Es plus 0.002. What is this value? This is the value of maximum tensile strain in steel. Again, it is difficult to visualize the failure in terms of strain. Let me simplify this in the form of deformation. We know strain is equal to, again, delta L by L. The maximum strain is 0.87 Fy upon Es plus 0.002, and consider the length of the beam is 3000. Okay. Now take Fe415 steel, and we know the modulus of elasticity of steel is 2 into 10⁵ Newton per mm square. Just put the values. Fy is 415. Es 2 into 10 raised to 5 plus 0.002 delta L upon 3000. In this way, we get the delta L 0.87. 3000. So we get delta L 11.42 mm. Right? Now, what does 11.42 means? It means when load is applied on the beam or beam is subjected to some load, and due to that load in tensile reinforcement, the tensile deformation goes beyond to 11.42 mm, it will fail in tension. So this is the simplest explanation of strain in the form of deformation. Now we are going towards the stress diagram. Okay, before that stress diagram, we know that in WRC beam, reinforcements are also provided in the compression zone, and the reinforcement in the compression zone are provided at d dash distance from the top of the beam. And if you want to know how much strain will be at the distance of d dash, means how much strain will be at the place of compression steel, so that we can find using the triangular rule. Say, I just draw here, and this is the depth of neutral axis. It will be XU, right? So this is 0.0035. This is XU, and this is D dash, right? So what will be this height? This is XU, this is D dash. So I can write XU minus D dash, right? So using triangle rule, 0.0035 upon this horizontal distance upon this vertical distance is XU is equal to this horizontal distance. Our interest is to find this value. Let us denote this A. So A upon, so this horizontal line upon this horizontal line, XU minus D dash. That's why 0.0035 XU minus D dash upon XU is equal to A. So the value of strain at the place of compression steel will be 0.0035 XU minus D dash upon XU, right? So this value 0.0035 XU minus D dash upon XU. So this is all about the strain diagram of WRCB. Now let's move towards stress diagram. Stress diagram will be like this. This is 0.446 FCK. This will be C1, and this will be T1, and this distance will be 0.42 XU. Stress diagram simply RC balanced section. As we have already discussed, doubly RC beam is the combination of singly RC balanced section and auxiliary section. So in stress diagram, first we will see the stress diagram of singly RC balanced section. Okay. Now, when we see the singly RC balanced sections stress diagram, first 0.446 FCK comes into the picture. Now, what is this 0.446 FCK value? So 0.446 FCK is the maximum compressive stress in concrete. In other words, we can say that when compressive stress in the beam exceeds 0.446 FCK, beam will fail in compression. Again, it is quite difficult to visualize the failure of the beam in terms of stress. So let me simplify this in the form of deformation so that we can get the clear idea. We know that stress sigma is equal to P upon A. Now maximum stress is 0.446 FCK and P, our interest is P, and area. Now just as for example, take B equal to 300 mm and D equal to 600 mm, and this depth and depth of neutral axis, just take XU is equal to say 250 mm, right? So what will be the area of this is 300 into 250, that's why, and take M20 grade concrete. So 0.446 FCK is equal to P upon 250. When we calculate this, FCK into 20 into 300 into 250, we get P equal to 669 into 10 raised to 3 Newton is equal to 669 kilo Newton. What does that mean? It means when beam is subjected to a load beyond that 669 kilo Newton, beam will fail in compression if M20 grade of concrete, width of beam is 300, depth of beam is 600 mm, and depth of neutral axis is 250 mm. Right? Now, in this diagram, we can say that at the top of the beam, there will be maximum compressive stress. When we goes down, it remains constant, right? Stress will remain constant up to certain distance, and that distance is 0.42 XU. Then it suddenly decreases and it will become to zero at the place of neutral axis. And T1 is the maximum tensile force in tension zone, or you can say maximum tensile force. And the C1 is the maximum compressive force. And the value of C1 is 0.36 FCK B into XU. Now let's see from where the value of C1 0.36 FCK B into XU has come. Now, what is C1? First, let me tell you what is C1. C1 is the total compression force. Now, total compression force means what? We know that the upper portion of the neutral axis is all about compression. We have already learned about center of gravity. I think we know the concept of center of gravity. What is the center of gravity? A point where we assume that the entire weight of the body is assumed to be concentrated. Or you can say that a point where resultant of all the forces is assumed to be concentrated. So C1 is nothing but the resultant of all these compressive force. Yes, again I repeat, C1 is the nothing but the resultant of all these compression force, and it is assumed to be concentrated at the distance of 0.42 XU from the top of the beam. Now let me explain from where the value of 0.36 FCKB into XU has come. Let me draw the stress block here. This is 0.446 FCK. Say this is the width of the beam. This is C1. This height is XU. And this height is 0.42 XU. Now what about this height? If this whole height is XU, this height is 0.42 XU, when we do 1 minus 0.42, it means this value comes 0.58 XU. XU minus 0.42 XU, it will come 0.58 XU. So to find the value of C1, let us consider this rectangular as a whole rectangular. Now we know that stress is equal to what? Force upon area. What we need? We need P. We need force. Our interest is P. The sigma into A equal to P. It means when we multiply area with stress, we will get the value of force. Now sigma. Sigma is what here? 0.446 FCK into area is what? First we take the whole area, and the area of whole rectangular is B. This is B and this is XU. Again I repeat, sigma is what? Stress available is 0.446 FCK. Now the area of rectangular is B and this XU minus, for getting the value of C1, we have to deduct this portion, means this portion look like parabola. So from this whole rectangular, we need to deduct this parabola minus stress is what? 0.446 FCK into area. The area is 1/3 into BH, 1/3 into B is P, and the height is what? The parabola height is 0.58 XU is equal to P. Means what we have done? We have deducted the stress block of parabola from the stress block of rectangular is equal to, that's why 0.446 FCK B into XU minus, when we calculate this 0.446 into 0.58 divided by 3, we get 0.086 FCK B into FCK is equal to P. Now this FCK B into XU are the common. So 0.446 minus 0.086, we get 0.36 FCK B into XU is equal to P, and we donate force is equal to what? Total compressive force C1. So in this way, we can calculate the total compressive force C1, right? And it will come 0.36 FCK P into XU. Similarly, T1, 0.87 FYAST. Now, point from where 0.87 FYAST come. Let's see that. See, stress is equal to P by K. We need to find the force sigma into A equal to P. Now, what is the permissible stress in steel? It is IS code recommend that it is 0.87 FY. And what about A? In tension zone, we consider that all tensile force is due to the reinforcement that we have provided in the tension zone. It means the area of tension zone is what? AST is equal to P, and we donate P equal to here T1. So in this way, it comes 0.87 FY AST. And the vertical distance between total compressive force and total tensile force is called Z. Z is called lever arm. And in this diagram, we can clearly see that this whole distance is what? Effective depth. This whole distance is what? D. So if we deduct 0.42 XU from effective depth, D minus 0.42, we get the lever arm Z, which is the vertical distance between total compression force and the total tensile force. So this is all about the stress diagram of singly RC balanced section of doubly RC beam. Now let us see what is the stress diagram of auxiliary section. Diagram remains same, but the value changes. Maximum stress is 0.446 FCK. This is C2 and this is T2. Okay. Now C2. Here C2 is what? Total compression force in auxiliary section. Right? And in auxiliary section, compression reinforcement are placed at D dash distance from the top of the beam. So again, if we want to find the value of C2, it's a stress. Sigma is equal to what? P by A. Sigma into A equal to P. Our interest is P. Sigma is what? 0.44 FCK. No. Here 0.446 FCK is what? Maximum compressive stress in concrete. But this auxiliary section is all about the compression reinforcement, right? So what is the stress in this compression reinforcement at the level of D dash? So it is denoted at FSC. FSC means stress in steel and compression zone into area. Area is what? This compressive force is due to the compression reinforcement that we have provided in the compression zone. It means area ASC, area of steel in compression, is equal to P, and we donate P is equal to C2. So equation of C2 comes FSC into ASC, right? Some book has denoted C2 is equal to FSC minus FCC into ASC. Now what is FCC? FCC is the stress in concrete in compression zone. But what IS has recommended that the value of FCC is very less which compared to the value of FSC. That's why IS has recommended to neglect the value of FCC. It's up to you. You can consider FCC or you can neglect the XCC, but just follow the IS 456, and that equation comes C2 equal to FSC into ASC. Now, what about T2? T2 is nothing but the reinforcement in the auxiliary section. I mean, in tension zone of the auxiliary section. Again, T2 is equal to sigma equal to P by A. Sigma into A equal to P. Sigma is what? This is all about the reinforcement. And IS has recommended that the permissible stress is what? 0.87 Fy into A means AST2 is equal to P. So we donate P equal to again T2. So the equation of T2 comes 0.87 Fy AST2. Now the vertical distance between C2 and T2 means total compression force and total tensile force is Z, but we denote Z as Z2 and this Z1. So what will be the equation of Z2? Total depth is D, and if we deduct D dash from the D, we get the lever arm Z. So the equation of Z2 will become D minus D dash, right? From this stress diagram, if we want to find the moment of resistance of the WRC beam, means how much moment WRC beam can carry, so we can make the equation from this stress diagram. Moment of resistance, moment is what? Force into perpendicular distance. So the force is what? C1. C1 into what? The vertical distance is Z1 plus C2. And the vertical distance is what? Z2. Using this equation, C1 Z1 plus C2 Z2, we can find the moment of resistance of the WRC beam. C1, we know that 0.36 FCK B into XU, Z1 D minus 0.42 XU plus C2 FSC into ASC and Z2 D minus D dash. So this will be the equation of moment of resistance of the WRC beam. So this was all about the stress strain diagram of WRC beam, right? So today I stop here. Thank you.